Welcome to the lab demonstration on configuring OSPF version 2 in a single area on Ruckus ICX switches. In this video, I'll demonstrate how to enable OSPF globally and on interfaces of ICX layer 3 switches. I'll show you how to display information about OSPF neighbor states. I'll display debug information that displays the neighbor adjacency process. I'll show you how link speeds can impact, or in some cases not impact, an OSPF router's choice for best path when multiple paths are available. And finally, I'll show you the contents of the Link State Database, or LSDB, in a single OSPF area. This is the lab topology I'll be working with in this demonstration. It consists of 5 routers and 1 switch. The switch exists between 3 routers to provide a single broadcast domain for all 3 routers to establish adjacency over. All IP interfaces are configured, including the loopback addresses that are shown here and the interface addresses shown on each router. I'll be enabling OSPF on each of these routers and showing the process of establishing neighbor adjacency and showing the contents of the link state database. Later, we'll be adding a dedicated link between R5 Seattle and R3 San Jose to show how link speed impacts path selection with OSPF routers. Okay, let's get started. OSPF is enabled on a Ruckus ICX switch by first enabling the router OSPF process in the global configuration context. And that's the router OSPF command. And then we need to define the areas that this router is going to participate in. So since this is a single area demonstration, it'll have to be the backbone area, which is area 0. So we do that with the area 0 command. Now we have to run this on each of the routers in the lab topology. I've already taken the step of configuring it on the other routers, as I'll show here. So in San Jose, we've already configured router OSPF in area 0. In San Diego, the same. In Seattle, the same. And in Portland, the same. So all routers have OSPF enabled globally, defined in area 0, but none have any interfaces that are participating in OSPF at the moment. So let's go ahead and get started with that. So on the Salt Lake router, the interface that is connecting into the network is the 113 interface. And it already has an IP address configured on it. So we just need to enable OSPF. And that's done with the IP OSPF area 0 command. Now this interface actively participates in OSPF and will immediately start sending hellos out to neighbors. So let's go ahead and do this on the other routers as well. The San Jose router has one interface as well. It's Ethernet 114 that connects into the backbone switch. In that interface, we run the same command, IP OSPF area 0. We can shorthand those commands a little bit to just save ourselves some time and not have so many typos that I tend to make as we go through these lab exercises. Okay, and on the R4 router, we have 2 interfaces to configure for OSPF, one connecting to the Salt Lake City router and the other connecting into the backbone switch. So we'll go ahead and configure those now. Those are interfaces 1/1/3 and 1/1/11. And we'll use the up arrow to save us a little bit of time in making these configuration changes. And now both interfaces are in area 0. The R5 Seattle router also has 2 interfaces. These are 111 and 115. At this point, the 1/1/5 interface is not going to be enabled. We're going to enable that in just a little bit to go ahead and show you the neighbor adjacency process and how that happens. We'll enable OSPF, but the actual interface, the 1/1/5 interface, is in a disabled state right now. Okay, that one's ready to go. And let's do our last router, R7 Portland. That one has one interface, and that's 115. and this is the interface that connects back to Seattle, but right now, as I said, the interface in Seattle is disabled, so there will be no OSPF adjacency on this interface at the moment. Now let's look at OSPF adjacencies between these routers. So we'll start in the Salt Lake router. We check this with the show IP OSPF neighbor command. And we have one neighbor in Salt Lake, which makes sense. It only has one link back up to the San Diego router. And we see that that is in a full and BDR state. So let's go check on the others. Okay, in San Jose, we've got two neighbors, which is correct. From San Jose, we should be establishing a neighbor adjacency with San Diego and Seattle. And those look to both be up and in a full state. We'll move over to R4 San Diego, and we should have three neighbors here, which is correct. We have a neighbor adjacency with Salt Lake on that single link, and we have a neighbor with the two other routers on link 11, which is San Jose and Seattle. We'll check in Seattle. And we have two neighbors here in Seattle, which is correct. These are going to be San Jose and San Diego on the 1.1 interface that goes into that shared switch in between them. And if we go over here to Portland, just to check, we shouldn't have any neighbors here because this link is down. But just to check, so right here we have no OSPF neighbor entries because it hasn't gone through a neighbor adjacency process and synchronized databases with any routers because that link is down on the Seattle side. So let's go ahead and view that neighbor adjacency process between Portland and Seattle here. So we'll go in here, and on the Portland router, we will get back out here and we'll run the debug IP OSPF packet command. Now that the debug's enabled, we'll go ahead and go over to the Seattle router and we will enable this interface 115 and watch the debug process. Here we see outbound hellos. I'm now receiving hellos. Those are from the 192.168.50.2, which is going to be the Seattle interface. And now we're exchanging a lot of information, so I'm going to let this continue on for a moment, and then we'll analyze some pieces of information that we're seeing in this output. Okay, now we're back to just sending and receiving hellos. So let's go ahead and turn off the debug. And that's done with the undebug all command. We get messages letting us know that all of the debugging has been turned off. Okay, so let's go back up and see what we've got. So up here we see several hellos sent and received between the two routers. And once they've gone through the hello process and confirmed information that are required for it to move to the next step, each router begins sending and receiving database descriptors. These database descriptors are a summary of the network as each router knows it. Some of these things they'll both already have information for, and some will be unique to each. Those database descriptors will lead to link state requests being sent and received on both routers to request more information about the data that was provided in the database descriptors. Each of those requests will be replied to with a link state update, and those link state updates are sent based on the requests that were received on each of the routers. After those updates, each router will then send link state acknowledgments confirming they received information in the updates and that it's identical to what was provided to them, and they'll send that information back, and then they go back to sending regular hellos to each other. So that is the neighbor adjacency process of OSPF routers, and through the debug OSPF packet output, we can actually see the entire process and everything that's exchanged. So up until now, we've had a pretty simplistic OSPF network topology with single paths between every router in the network. But we're going to go ahead and add a link between the R5 Seattle router and the R3 San Jose router. This link is going to be given the IP addresses shown here on the topology on interface E11 on both routers. So before we configure any interfaces or OSPF on this new link we're putting in between San Jose and Seattle, let's go ahead and take a look at San Jose's routing table, and we're going to look for the 192.168.50.0 network, which is the link between Seattle and Portland right now. So let's take a look at that. The show IP route command shows the route table, and we see the 192.168.50.0 network in our routing table, and the next hop is 192.168.20.2, which is the interface, the only active interface into that layer 2 switch that connects San Jose to Seattle. So that's on its 114 interface. So that's what the routing table looks like right now before we enable the link between Seattle and San Jose. So let's go ahead and get that configured. So that's interface 11, and we're going to give it 192.168.30.1 with a 24-bit subnet mask. And once we do that, we need to put it in OSPF area 0, so we do that with the IP OSPF 0 command. Okay, we are good to go. Actually, one other step for us, because this interface is disabled, the cable's already in place, we have to enable 1111. Okay, let's make the same change over in Seattle, which is our number 5 switch. That's also E11. And we're giving it the 30.2 address with a 24-bit mask. We need to enable OSPF and enable the port. Okay, let's go ahead and take a look from here and make sure that our neighbor adjacency is coming up. And that's the show IP OSPF neighbor command. So we're still in a init state, so they haven't completed the process of synchronizing link state databases at this point. We'll just run that command again until we show that we're full. So now we're exchanging information in a two-way state. And any second now, we should be up to full. So they're in exchange state, and now we're full. Okay, so all of our neighbors are up. We have a new interface up between Seattle and San Jose. And let's go ahead and take a look now at what our routing table looks like. So for the 192.168.50 network, we've got two paths. Those two paths are through the different links. They both go through Seattle, but one goes through the switch and the other goes through Seattle. Let's look at those link speed differences between the two different paths we have here. So we can do this with the show interface brief command. And what we see is we're using ports 4 and 11. So 4 is operating at 100 meg, and 11 is operating at 1 gig. So we don't want these to be equal cost. We would prefer that the traffic always be going over the higher speed link over the lower speed link. So we don't want these to be equal cost because they're not actually equal. OSPF bases cost on the speed of a link, but unfortunately when OSPF was founded, they used a reference bandwidth based on 100 meg link speed. So this 100 meg link speed, what this meant is that any link faster than 100 meg always showed up at the same cost. There is no better cost than a 100 meg link. So what we've done here is we allow the ability to change that reference bandwidth value to something more reasonable within your network so that you can more accurately reflect cost of links that are higher than 100 meg. So we're going to go ahead and do that in just a minute here. To make that change, we adjust a parameter under the router OSPF configuration context called the AutoCost reference bandwidth command. So let's go ahead and jump in. We have to do this on all the routers in the network if we want to make sure that they're all using the same base cost, determine link speed throughout the network. So we're going to jump through each of the routers in the network, and we're going to go ahead and make this change, and we're going to set the AutoCost reference bandwidth. So let's see, in Salt Lake, we need to get into configuration mode, router OSPF, and from here we run the command AutoCost reference bandwidth, and we're setting it to 1,000. The link speed that we were operating at is a 1 gig link, so we'll just set it to the highest speed link within our network at 1 gig, and that will be the reference value for the equation that determines the cost of a link in OSPF. So let's go ahead and do this on each of the routers. Okay, done in San Jose, done in San Diego, done in Seattle, and finally done in Portland. So let's take a look at this now. Now that we've done this, we want to go back and take a look at San Jose and see what our route looks like. So we're in the show IP route command, and now we only have one route to the 192.168.50.0 network, and it's through the 30.2 interface, which is the direct link between San Jose and Seattle. So it's looked at that interface and said it's a lower cost than the other interface available to me, so I'm going to prefer that, and they're no longer equal cost. Okay, so now let's take a look at the OSPF database. The OSPF database is a collection of all the information of all the OSPF routers in an area that established essentially the map of the entire OSPF area and all the routes that are available in it. This database should be the same database on every router in the network. So we're going to go ahead and run the show IP OSPF database link state command, and we're going to confirm that indeed each of these has the same view of the network in our topology. So here is the output here. What we have is we have 1, 2, 3, 4, 5 router LSAs, which is correct. We know we have 5 routers. We have Salt Lake City, San Diego, Seattle, San Jose, and Portland. So those are our 5 routers. And we have 4 networks that interconnect all of them. The 192.168 networks of .10, .20, .30, and .50. So this looks good to me. Now this information should be the same in every one of our routers. So let's go take a look. So 5 router LSAs, 4 network LSAs. So in San Diego, same information, same database. Same in Seattle, and same in Portland. So this just confirms that all of these routers are fully adjacent. They've fully exchanged information about every network that they know and everything they're connected to, and they've exchanged that information with their neighboring routers who share with their neighboring routers to establish a full topology in the single link state database. So this concludes the lab demonstration on configuring OSPF in a single area using Ruckus ICX switches. What we walked through was configuring OSPF globally and on interfaces of these switches. We displayed information about OSPF neighbor states, We looked at debug information showing the neighbor adjacency process. We watched how link speeds can impact the routing decisions made by OSPF routers, and if they're not adjusted for current speeds in the network, they might create some problems for you and some unexpected behavior. And then we took a look at the link state database, which, because this is a single area, we really only have router and network LSAs because we don't have any adjoining areas to provide those other types of LSAs. So this presentation was useful for you, and thank you for watching this demonstration.